12, we'll continue talking about probability and describe the general rules of probability. Some of the concepts: independence and the multiplication rule, the general addition rule, conditional probability, and the general multiplication rule. So everything in this chapter actually follows what we learned in chapter 10. The probability of any event is between 0 and 1. If S is the sample space, then the probability of S is equal to 1. In other words, all the probabilities add up to 1. If A and B are disjoint, then the probability of A or B occurring is the sum of their probabilities. And for any event A, the probability that A doesn't occur is 1 minus the probability that it does. Sometimes it's helpful to draw a picture to show the relationships among different events. The picture we're going to use is called a Venn diagram. So here we have two disjoint events, A and B. We indicate this by sort of showing that they don't overlap. Two events that are not disjoint have outcomes that are in common. So here A and B overlap. Okay, here's a multiplication rule, just to sort of give it a bit of a background. In a 2012 article, the New York Times reported that 30% of Americans have bachelor's degrees. So suppose we pick two Americans at random. What is the probability that both people hold bachelor's degrees? And we can think about it this way. Let's think about all the possible pairings of people. In 30% of the pairings, the first person chosen has a bachelor's degree. So we indicate that with a Venn diagram. Of the pink, the entire population, the blue oval represents the 30% of people who have bachelor's degrees in the first grouping. So of this group, 30% of the second people have bachelor's degrees. So that's 30% of 30, or 0.3 times 0.3 equals 0.09. That's the probability that both people have bachelor's. If two events A and B do not influence each other, and if knowledge about one doesn't change the probability of the other, the events are said to be independent of each other. And the multiplication rule for independent events: the probability of A and B occurring equals the product of their probabilities. And that's only if A and B are independent. We'll talk about another case. Okay, now we'll get to the general rule for addition. We had that if events A and B are disjoint, then the probability of A or B equals the probability of A plus the probability of B. Now, in the case where A and B are not disjoint, they overlap. And essentially, if we just add the probability of A and the probability of B, we're basically adding that overlapping region, we're adding that twice. So to correct for that, we take away one of the occurrences where it overlaps. So we only count it once. So the general rule for any events A and B is the probability of A or B occurring equals the probability of A plus the probability of B minus the probability that they occur together. In other words, the overlap. So we're correcting for that one, for double counting there. Notice if events A and B are disjoint, as in the top illustration, then the probability of A and B occurring, there is no overlap. So that probability is 0. So this rule works in the case where A and B are disjoint as well. That's why we call it the general rule. Now we're going to talk about conditional probability. So suppose we have, in the 113th Congress, there were 233 Republicans, 200 Democrats, and 2 vacancies at the beginning of the term. There are 78 women in the House, 58 are Democrats, 20 are Republicans. There are 433 occupied seats in the House. So we'll summarize this in this table. Now, we can fill in the totals for the rows and the columns. Notice in the bottom right, 433, that's the total number of occupied seats. Okay, if we select a person at random from this group, what is the probability that person is a woman? Well, there are 78 women out of 433 people, so 78 divided by 433, it's about 18%. Now, if we select a person at random from this group, what is the probability that a person is a Democrat? And once again, there are 200 Democrats, so we have 200 divided by 433 is about 46.46. Now, one more. If we select a person at random from this group, what is the probability that the person is a man who is a Democrat? So again, we are picking one person from the 433. What's the probability that the person is both a man and a Democrat? Well, there are 142 men who are Democrats, so 142 divided by 433, about 0.33. Now, suppose we select another person at random from this group. Assuming the person is a woman, what is the probability the person is a Democrat? So this question is different from the previous questions. There is a condition involved. We are told in advance that the person we've chosen is a woman, so we consider only the women. So of the 78 women, what proportion are Democrats? There are 78 women, 58 of whom are Democrats, so the probability is 58 divided by 78, or 0.74. Now, suppose we select another person at random from this group. Assuming that the person is a Democrat, what is the probability the person is a woman? This time the condition is that the person is a Democrat, so we consider only the Democrats, not the Republicans. Of the 200 Democrats, what proportion are women? Well, there are 200 Democrats, 58 of whom are women, so 58 divided by 200 is about 0.29. In the first problem, we asked, assuming that the person is a woman, what is the probability that the person is a Democrat? This is the same thing as asking the question, what is the probability the person is a Democrat, given that she is a woman? So again, we get the calculations, and in this case, we can write this in the notation shown here. The probability a person chosen is Democrat, given that the person is a woman. In the second problem, we asked, assuming that the person is a Democrat, what is the probability the person is a woman? And we can ask that question a little bit differently as well. What is the probability the person is a woman, given that she is a Democrat? So the condition is that she's a Democrat. That's given. And again, we can calculate the probability here. This is written, notice it's basically the opposite of the question above. This is the probability a person is a woman, given that the person is a Democrat. Okay, here's a slightly more complicated problem. All athletes participating in sports at Low High School must submit to drug testing. Those who fail the test are suspended from competing the following year. Suppose the drug test is 95% accurate, and let's assume that 4% of the athletes actually use drugs. What is the probability that an athlete is falsely accused? So to simplify things a little bit, let's just pick a nice round number and apply it to the probabilities and the percentages. So let's just assume there are 1,000 students. And we'll ask some questions. What is the number of students who use drugs? Well, 4% of the 1,000, around 40. What is the number of students who don't use drugs? Well, 96% don't, so 960. Okay, so we expect that 40 students use drugs and 960 don't use drugs. Now, the test is 95% accurate. That means that 95% of those who are tested will be correctly identified. So 95% of the drug users will test positive, and 5% of the drug users will test negative. Also, 95% of the non-users will test negative, and 5% of the non-users will test positive. So how many of the users will test positive? Well, 95% of 40, or 38 of them, will be correctly identified. How many of the users will test negative? 5% of that 40, or 2 people, will be getting away with something. How many of the non-users will test negative? 95% of the 960, so 912 will be correctly identified as being non-users. And how many of the non-users will test positive? 5% of 960, or 48. Now we'll enter this information into a 2x2 table like we had in the example with the Democrats and Republicans. So we have the categories of those who use drugs, those who don't use drugs, and those who test positive, and those who test negative. Be sure you understand where all of these numbers came from and where they go. So, the question was, what's the probability of somebody being falsely accused? And in this case, that translates to mean, given that a student tests positive, what's the probability that he or she doesn't use drugs? Or symbolically, we write that as the probability of a non-user, of picking a non-user, given that the test is positive. So in this case, there are 48 who don't use drugs, but who will test positive out of the total of 86. So roughly 56% of those who test positive are falsely accused. Now, we'll state all the probabilities from the table symbolically. Probability a person is a user is 0.04. That's 40 out of 1,000. Probability of a non-user is 0.96. Probability someone tests positive, 86 out of 1,000. Probability someone tests negative, 914 out of 1,000. Probability that someone is a user and tests positive, 38 out of 1,000. Probability of a user and tests negative is 2 out of 1,000. Probability that someone's a non-user and tests negative is 48 out of 1,000. Probability someone's a non-user and tests negative, 912 out of 1,000. So we have all of these numbers. What we're going to do here is actually develop a general rule for probability that includes conditional probability. So, for example, the probability that someone is a non-user given that they test positive is 48 out of 86, or 0.56. We can also note that this is equal to the probability someone tests positive and someone's a non-user divided by the probability someone tests positive. Notice, probability that someone tests positive and is a non-user is 0.048. Probability a person tests positive, 0.086, and we get the same result. This is an example of what's called the general multiplication rule for probability. And it can be written two ways. The probability of event B happening, given that event A has happened, equals the probability of A and B happening divided by the probability of A. Or we can write this as the probability of A and B equals the probability of A times the probability of B given A. Notice how the last one is actually basically the multiplication rule we had before. The difference is we're using the conditional probability for B. So the definition of conditional probability reminds us that in principle all probabilities, including conditional probabilities, can be found from the assignment of probabilities to events that describe a random phenomenon. The definition of conditional probability then turns into a rule for finding the probability that both of the two events occur. So here again, we'll restate the general multiplication rule. Probability of A and B occurring together is the probability of A times the probability of B given A, where the probability of B given A is the conditional probability that event B occurs given that event A has already occurred. Note, the two events A and B are independent if the probability of B given A equals the probability of B. That is to say, the probability of A doesn't affect the outcome of the probability of B when A and B are independent. So in this case, the probability, in our example, the probability someone is a non-user is 96%, 0.96. And the probability someone is a non-user given that he or she tests positive was 0.56. Since these two probabilities are not equal, these events are not independent. So one event influences the probability of the other event. So this means that knowing whether a test result is positive affects the probability that a randomly selected person is a non-user. So to review, we defined independent events. We determined whether two events are independent. We used the general addition rule, define conditional probability, compute conditional probabilities, and applied the general multiplication rule.